So in this lecture, we are going to look into the process of neighbor discovery. So let's start with two different scenarios. First, you enter a shopping mall and you would like to see if there is a Wi-Fi service that you can connect to. How does your phone discover the presence of Wi-Fi networks? The second example is that you have small IoT devices that are equipped with sensors and can they communicate over low power wireless links, such as using protocols of Zigbee or Bluetooth. And these IoT devices are deployed in the environment and they're also carried by people. How would these devices discover each other and also do it in a highly energy efficient manner? Because these devices would be operating on batteries. So how do you perform neighbor discovery? It is easier to perform if, for example, there were no constraints and all the devices were always actively active and always powered. So they were not duty cycling. But of course, we don't want to do that, because if we don't do a duty cycle, or if we don't sort of like, if we keep them active all the time, then we'll run out of battery very quickly. So how are the key challenges? That we want to design a protocol that is highly energy efficient, where devices are off for most duration of the time, and yet they can perform the neighbor discovery very efficiently. And there are two methods for neighbor discovery, that are synchronous and asynchronous. So let's look into them in detail. In synchronous neighbor discovery, all nodes are synchronized to the same clock or time, which means that they have the same notion of time. And this mechanism works by having nodes wake up periodically at the same time and then transmit or receive packet to perform the neighbor discovery. For example, if let's say there are two nodes A and B who want to discover, node A would discover B when it hears transmission from the node B and vice versa. If you look at another example where time is divided into slots of 100 millisecond, and let's say the global time reference is T naught, each node would wake up every 100 milliseconds to exchange packet and discover each other. So this is a good example of synchronous neighbor discovery. Synchronous neighbor discovery, however, has a major drawback as well. Firstly, the synchronization process is typically very expensive and requires node to periodically resynchronize and correct their clock drift. And this can lead to increased energy consumption, and also could lead to a lot of traffic or packets being exchanged, and all of which is something we would like to avoid, especially on battery operated devices. So to give you an analogy for clock drift, imagine if there are a group of people who are trying to meet at a specific time. Some people watches are running faster than others, and if they don't periodically resynchronize their watch, they will eventually be out of sync and arrive at very different times. Similarly, in synchronous neighbor discovery, nodes need to periodically resynchronize and correct for clock drift to avoid going out of sync. Secondly, since all the nodes wake up and sleep at the same time, it can also lead to collisions if they start to transmit at the same time. To give you another analogy, imagine a group of people who are trying to cross a narrow bridge at the same time. If everyone tries to cross at once, it will lead to traffic jam and slow down the process. Similarly, if all nodes try to transmit at the same time in synchronous neighbor discovery, it will lead to collision and slow down the discovery process. So there are also examples of synchronous neighbor discovery where there are asymmetric nodes. This means that some nodes are more powerful than other. A good example is Wi-Fi network. In the Wi-Fi network, the access point is typically always on, whereas the mobile phone and other such devices are duty cycling and they are typically sleeping for most period of time. In this case, one way to implement neighbor discovery would be for mobile device or an access point to send a beacon and wait for reply from the other party. However, this also introduces a second problem that we might have to think about, is that typically these end devices would be sleeping to conserve energy by going to sleep mode when there is no data. So how when it's going to sleep, how would you basically, let's say, it's like, how would you basically, when it is sleeping, figure out that there is a data that is at the access point for it to access? And this is also something important that this neighbor discovery process has to sort of like look for or tackle. So Wi-Fi networks have very similar issues. So access points are highly capable. So one way to that the Wi-Fi network implements this is that it implements something called power save mode. And what it means is that when a mobile device wants to save energy, it goes into low power mode and it sends a message and informs the access point before going to sleep state that I'm going to be going to sleep state. So what does the access point do? That any message that arrives at the access point when the end devices are in the sleep mode are stored in its buffer, and access point periodically sends something called traffic indication map to inform the end device of incoming packets that have been buffered. And when eventually the end device wakes up, then the access point sends this message to the end device. And we show this in this graph, this process happening in the device. So now let's talk about asynchronous neighbor discovery protocols. In asynchronous neighbor discovery protocol, there is no time synchronization required among the nodes in the network. And this is greatly applicable for very constrained devices such as IoT devices, because you don't have the overhead of exchanging messages for time synchronization. So as the asynchronous protocol does not have a central entity or device to provide also synchronization. So how does it work? The nodes can decide at different time slot to wake up, transmit, and listen for messages. And under these conditions, the question becomes like, how long would it take for the nodes to discover each other when they are not synchronized to each other? And the answer is a bit more complicated. So to look at this, let's look at something called a birthday paradox. So what is birthday paradox? It means that if we have, let's say, a group of n people, what would be the probability that there is at least one pair of people who have the same birthday? And what we find is that as the number of people in the group increases, the probability that there is a pair of people with the same birthday also increases. The birthday protocol, which is a neighbor discovery mechanism that sort of like builds on this concept, actually builds on this idea to achieve very short time neighbor discovery. So what it does is that it divides the time into slots of equal length, and these slots can be sort of like thought of representing birthday in the paradox. Now, if each device in the network would randomly select one of the available time slot for its transmission, and this could be looked at like a person having a random birthday. Now, if let's say during each time slot, a device would either transmit a beacon signal or listen for beacon from the neighboring device. Now, if two or more devices, for example, they select the same time slot for transmission, their signal will collide, which is something we want to avoid. But if let's say they receive the transmission, then the neighbor discovery process happens. So what happens is that the device continues to randomly select and transmit in the time slot until all the neighboring nodes have been discovered. And this process needs to be typically repeated multiple times to ensure high probability of successful neighbor discovery. And once a device discovers its node, it can establish communication and synchronize and enable the data exchange. So the birthday paradox helps us to speed up the neighbor discovery process, as the probability of two devices choosing the same time slot increases rapidly as the number of devices and the slots in the network. And this leads to high likelihood of successful transmission and being able to discover the nodes in a network in a deterministic manner. So there is another kind of asynchronous protocol that can ensure deterministic discovery time. And this is, we can give one example. This is called Discord. So this protocol makes sure that nodes wake up as at a multiple of some prime number. And in this research paper, which was published in Census in 2008, they demonstrate that this can ensure deterministic discovery time for the neighbor discovery process. As an example, if a node I picks a prime number pi and wakes up pi time slot, and then there is another node pj which picks a prime number pj and wakes up at pj time slot, we can actually sort of like calculate that the worst case time when they select the same time slot would be pi and pj, which actually controls the time at which the neighbor discovery process would lead to these two nodes discovering each other. However, there is a caveat, and that is that in this protocol, if the nodes pick the same number, they may never converge. And this is something that we should keep in mind, that these nodes have to select two different prime numbers. Hence, we can summarize this by saying that we can divide these neighbor discovery protocols, which are asynchronous, into two categories. One is probabilistic. Example is building on birthday paradox. Another could be deterministic. Similar one protocol that we talked about was Disco, but there are also other protocols that we list on the slide. With this, we come to an end of this lecture. Thank you.